In the Phi-4-reasoning-vision-15B technical report released by Microsoft Research, we are looking at a compact 15 billion parameter open-weight multimodal reasoning model.
Right, a model that aggressively pushes the Pareto frontier of accuracy versus compute cost.
Exactly. It excels at scientific reasoning and computer-using agent tasks, like GUI grounding.
Which is a fancy way of saying it can actually navigate your computer's interface.
And it achieves this through a novel hybrid think-and-nothing architecture that selectively applies chain of thought only when a task actually demands it.
But most importantly for the field, this report proves that data quality entirely trumps raw scale.
Yes, it achieves highly competitive performance on just 200 billion training tokens. That is a mere fraction of the trillion-plus tokens used by massive peers like Qwen3VL or Gemma 3. Welcome to AI Paper Podcasts. Today's mission is to dissect exactly how Microsoft achieved these outsized results with such a limited compute budget. We are going to break down their specific mid-fusion architecture choices.
Their incredibly rigorous synthetic data curation pipeline.
Right. And the exact training recipe. So if you are an ML engineer or AI researcher listening to this deep dive, you can take these specific efficiency hacks and apply them directly to your own multimodal models.
So let's jump straight into the architecture. The overarching choice the research team made was to use a mid-fusion design.
Right. They combined a SIGLIP2 vision encoder, an MLP cross-modality projector, and the Phi-4 reasoning language model backbone.
Which, is a highly deliberate departure from early fusion models. If you look at early fusion architectures, they allow for unrestricted cross-attention between image patches and text tokens right from the very first layer.
Which sounds great in theory.
Oh, it is. That setup gives you incredibly rich joint representations of the data. But, and this is a big but, it demands massive compute and memory resources. It is incredibly heavy.
Yeah.
Mid-fusion keeps the visual and textual processing completely separate until they meet in the middle. The vision encoder acts as the eyes, converting images into visual tokens.
And the MLP projector acts as the translator.
Exactly, mapping those visual tokens into the language model's embedding space. Then, the LLM takes over the heavy lifting of the actual reasoning. This preserves the strengths of those pre-trained components without the crippling computational cost. It keeps inference fast.
And fast inference is obviously essential if you want an interactive agent.
Yeah.
But, and I think this is a crucial point from the paper, that speed means nothing if the agent is functionally blind.
Right.
If you are building a computer-using agent, CUA, to navigate complex desktop screens, dense tax forms, or, cluttered web browsers, it needs to be able to see tiny pixel-level interactive elements.
Which is the resolution problem.
Exactly.
Yeah.
To solve this resolution problem, the researchers ran a large-scale ablation study on a smaller 5 billion parameter test model to maximize GUI grounding performance. That's the model's ability to locate a specific button or text box on a screen. They tested a bunch of configurations. Dynamic S2, multi-crop with S2, and dynamic resolution. Let's translate some of that. What are we actually comparing here?
We are comparing fundamentally different philosophies on how to cram a massive high-resolution image into a neural network. Multi-crop physically chops the image into squares, passing each square through the encoders separately.
But the problem there is you often slice right through the middle of the very UI element you are trying to find.
Precisely. S2 methods, on the other hand, dynamically resize and tile the image, so the model gets both local detail and a global overview. It ensures the model doesn't lose the forest for the trees.
Right, but the definitive winner in their ablation study wasn't standard S2 or multicrop.
No, it was the dynamic resolution method, specifically using the NAFLEX variant of the SIGLIP2 encoder. They allowed it to process up to 3,600 maximum tokens.
Which roughly corresponds to a native 720p HD resolution.
Yeah, and that setup absolutely dominated, especially on the highly demanding ScreenSpot Pro benchmark, which requires pinpointing extremely fine-grained UI elements.
Wait, so if I'm an ML engineer listening to this, does this mean my massive state-of-the-art language model backbone is functionally useless for agentic tasks if I cheap out on the vision encoder?
Functionally, yes, absolutely.
Sure.
Accurate perception is a strict, non-negotiable prerequisite for high-quality reasoning.
You cannot reason about what you cannot see.
Exactly. Let's say you ask your agent to click a tiny gray drop-down arrow on a cluttered web page. If your vision encoder downsamples that image to save compute, that arrow becomes a 2-pixel gray blur.
Yeah.
No amount of massive LLM chain of thought processing, no matter how sophisticated, will magically allow the model to click the right button. Investing a heavy portion of your token budget into a dynamic high-resolution vision encoder pays massive dividends.
Speaking of token budgets, their training recipe completely defines industry norms. As we mentioned in the summary, they train this entire model on just 200 billion total tokens.
Which is incredibly lean.
Very lean. They achieved this by breaking the training down into 3 highly specific sequential stages. Stage 1 was purely MLP pre-training. They used a mere 1.4 billion tokens. The vision encoder and the language model were completely frozen in place. They only trained the MLP projector to align the visual and text embedding spaces. And the fascinating part is that the researchers explicitly noted that doing more pre-training in this stage yielded absolutely zero additional benefit.
Think of the MLP projector as a translator learning the vocabulary between the image model and the text model. Since it starts from a random initialization, it just needs a brief, focused warm-up phase with clean image captioning data.
Just to figure out that a picture of a dog maps to the word dog in the LLM's embedding space.
Right, and once it knows the vocabulary, reading the dictionary a million more times doesn't make it a better writer. Stopping at 1.4 billion tokens is a massive compute saver. Overtraining here is just burning money on GPUs for no performance gain.
Makes sense. Then we hit stage 2, the instruction tuning phase, which is where the real heavy lifting happens. They allocated 188.5 billion tokens here, making up the vast majority of the training.
And here, everything is unfrozen.
Exactly. The MLP, the vision encoder, and the LLM are all jointly trained. They used a massive mix of single-image visual instruction tuning data. We are talking visual question answering, intense math problems, GUI grounding, and optical character recognition.
This is the phase where they are teaching the model its dual nature. They are teaching it both direct, fast responses for simple tasks and slower chain-of-thought reasoning for complex tasks.
Yeah.
By unfreezing the entire architecture, they allow the model to build deep, intricate connections between the high-resolution visual features it's extracting and the complex instructions the user is asking it to follow.
Finally, we have stage 3, focused on long context and safety, utilizing just 12 billion tokens. This stage completely shifts gears away from single static images. It focuses on multi-image sequences, reading long documents, and responsible AI, or RAI, safety data.
Which is a critical transition point for any model intended for real-world deployment. Stage 3 is where the model moves from understanding an isolated snapshot to operating in a continuous, complex world.
Right, because if you were building a robotic agent or a web browser assistant, the environment is constantly changing based on the actions the agent takes.
It needs to understand that image A led to image B. And of course, cementing the RAI safety guardrails after the core capabilities are already locked in ensures the model remains aligned without degrading its foundational reasoning skills.
But I keep coming back to this. How do you get state-of-the-art results out of a measly 200 billion tokens? The answer really lies in their ruthless data curation and synthetic augmentation. Quality over quantity wasn't just a buzzword here.
It was the absolute rule.
The research team literally sat down and manually sifted through open source datasets. They spent about 5 to 10 minutes per dataset, classifying them into rigid tiers like excellent quality data, good questions with wrong answers, low quality questions, and low quality images.
And that manual verification step is something a surprising number of development teams skip. They just assume sheer volume will smooth out the noise. But if you feed your model bad ground truths, you get bad predictions.
What is particularly clever is how they handled that good questions with wrong answers tier. STEM datasets, math, physics, coding, they're notorious for this.
Oh, absolutely, because they are often scraped from random forums or poorly processed through optical character recognition from old textbooks.
Right. But instead of throwing that data away, they used GPT-4o and a 4 Mini to regenerate the correct answers.
It is literally AI training AI.
Yeah, they identified the structural value of the question, leveraged a frontier model to fix the broken ground truth, and appended that as the new gold standard for Phi-4-reasoning vision to learn from.
And they didn't stop there. They used some brilliant synthetic hacks to squeeze more out of the data they already had.
For example, they took complex math and science images and synthetically generated highly detailed text descriptions of them.
The goal was to teach the model how to explicitly interpret mathematical visual elements like graphs or geometric shapes, rather than just asking it to solve the problem outright.
They also made data do double duty by merging domain-specific question answering with explicit formatting instructions. So the model learns the domain knowledge and the required JSON or Markdown output format at the exact same time.
They also generated temporal what's changed data. They would take sequences of screenshots, say a file downloading on a desktop, and ask the model to identify what altered between frame A and frame B.
Which is huge.
Yeah.
For an AI agent navigating desktop interfaces, knowing when a progress bar disappears or a new window pops up is vital temporal reasoning.
Yeah, but there is a very specific technical detail regarding their synthetic data pipeline that is incredibly important for anyone building a spatial model, and that is coordinate normalization.
Oh, let's break that down, because bounding boxes can be an absolute nightmare to manage across different data sets.
They can be. The researchers solved this by normalizing every single spatial coordinate in their training data to a range of 0.0 to 1.0 relative to the dimensions of the image.
Right.
Think of it like giving the model a treasure map with percentages instead of footsteps. It doesn't matter if the user interface is displayed on a massive 4K monitor or a tiny low-resolution laptop screen.
Telling the model to click exactly 50% of the way across the screen and 20% down will always hit the exact same button.
Exactly. The model always outputs normalized coordinates, making its spatial reasoning completely robust and invariant to raw pixel dimensions.
Which naturally leads us to something that feels like a bit of a paradox. Let's look at the balancing act of training an agent to do radically different things. We have to ask the obvious question. If you train a model intensely on how to navigate a Windows desktop, find a search bar, and click Start, does it suddenly forget how to do differential calculus?
You are describing catastrophic forgetting. It is a massive hurdle in machine learning. Typically, when you push a model hard in one specialized direction, its performance in unrelated domains degrades rapidly.
The weights adjust to favor the new data, overriding the old knowledge.
Right. But the findings in this paper challenge that assumption entirely.
Yeah, the researchers ran specific experiments varying the ratios of math data and computer use agent data, or CUA data. What they found was that uniformly superior performance across all domains is absolutely possible within a single model.
They increased the math data by 3 times, and not only did it not hurt the computer use performance, it actually slightly improved it.
Wow.
Furthermore, when they added a highly specialized targeted dataset called Phi-ground, they saw a massive spike in GUI grounding scores on the ScreenSpot v2 benchmark without losing their math capabilities.
This directly challenges the prevailing scale is all you need myth. The idea that you just throw petabytes of unstructured, uncurated data at a massive cluster of GPUs and let the model sort it out.
Exactly. This research proves that by carefully, deliberately balancing your data mixtures, you can push a single, relatively small model to excel in highly distinct reasoning domains.
And what's remarkable is that the data imbalances they used were relatively mild. Math data never exceeded 7.5% of the total mix.
Yet, the model became highly proficient at complex equations without sacrificing a fraction of its ability to navigate a computer screen. It proves that targeted data curation is vastly more powerful than sheer volume.
Which brings us to perhaps the most unique feature of Phi-4-reasoning vision, the hybrid mixed reasoning approach. Let's talk about the latency dilemma. Chain-of-thought reasoning is incredible. If you ask an AI to solve a complex astrophysics problem, you want it to think step by step.
Yes.
But we've all used an AI that acts like a philosopher when you just want a simple answer. You ask it to read the total on a grocery receipt or click play on Spotify, and it generates 3 paragraphs of internal monologue about the nature of music before it moves the mouse.
And latency is the absolute enemy of interactive agents. A user will not tolerate a 5-second delay while an agent ponders the philosophical implications of clicking a drop-down menu.
Right. If an agent isn't snappy, the user will just grab the mouse and do it themselves.
Exactly. So, Microsoft's implementation to solve this is a hybrid approach. In their training data, roughly 80% of the data consists of non-reasoning, perception-focused tasks. These are tagged with a specific nothing token.
That token acts as a just do it button, signaling the model to give a fast, direct answer without generating any internal monologue.
And the remaining 20% of the data utilizes a think token, triggering that deep, multi-step reasoning for the complex math and science problems.
The brilliance of this setup lies in their starting point. They used an LLM backbone that was already capable of reasoning from its previous text-only training.
They didn't have to teach the model how to reason from scratch. It already knew how to do math and logic. They only had to teach it when to reason and how to ground that pre-existing reasoning in a visual context.
Which drastically reduces inference time token generation. It saves time, it saves compute, and it significantly lowers the cost of running the model in production.
And as a developer integrating this model into an application, you actually have control over this mechanism.
Yeah, if the model misjudges a task Say it tries to give a fast, nothing answer to a complex chart analysis, you can explicitly override its behavior by passing the think token directly in your system prompt.
Which provides a vital fallback mechanism for engineers. The model learns the boundary between when to think and when to act implicitly from that 80-20 data distribution.
But by exposing those tokens and putting the final control in the hands of the user, it makes the model highly adaptable to vastly different deployment scenarios, from high-speed web scraping to deep academic research.
Let's look at the receipts. How did they evaluate this, and how did it actually perform?
Well, they benchmarked it to find that Pareto frontier of accuracy versus compute. They used a framework called Eureka ML Insights and tested the model on NVIDIA H100 GPUs. But here is the critical detail. They ran these tests using a batch size of 1.
I want to highlight why that batch size of 1 is so crucial for anyone doing benchmarking. A lot of leaderboards will maximize batch size to show off incredibly high throughput numbers.
Processing hundreds of requests simultaneously.
Right. But if you are building an agent that interacts with a single user in real time, throughput is a vanity metric. Per query latency is the only thing that matters.
Because testing with a batch size of 1 accurately simulates the real interactive latency a single user will actually experience when asking the agent to perform a task.
And under those strict, realistic interactive conditions, Phi-4-reasoning vision outperforms similarly fast models, and it matches the accuracy of much slower, heavier, and vastly more expensive models on rigorous benchmarks like ChartQA, MathVista, and MMMU.
It is punching way above its weight class.
It serves as definitive proof that you don't need a massive, sluggish model to achieve state-of-the-art reasoning, provided your architecture is optimized and your data pipeline is flawlessly dialed in.
Of course, we need to look at safety, particularly the responsible AI data we mentioned in Stage 3. The model underwent rigorous red teaming. It was explicitly trained on targeted safety datasets like hateful memes and WildGuard.
And the results they report are extremely low defect rates during automated safety evaluations. Just 1.4% for text-to-text safety and 4.5% for image-to-text safety.
It is also important that we impartially report the limitations of this architecture, as outlined by the researchers themselves. While it is incredibly efficient at its target tasks, larger closed-source proprietary models still win out on broad, unconstrained generalist tasks where vast parametric knowledge is required.
Furthermore, despite the high-resolution dynamic vision encoder, Phi-4-reasoning vision can still occasionally miss extremely fine-grained visual details and highly complex, cluttered images. It is highly capable, but it is not flawless.
So what is the final takeaway for you as you head back to your own machine learning workflows? Microsoft's open-weight model is living proof that you can achieve top-tier multimodal reasoning without begging for a trillion-token compute budget.
The secret sauce isn't raw scale.
No. It lies in smart architecture, specifically utilizing dynamic high-resolution vision so the model can actually see the problem you are asking it to solve. It requires ruthless, meticulous data curation, leveraging larger AI models to clean your ground truths, and augmenting with highly descriptive synthetics.
And finally, it is about giving your model the hybrid ability to simply not overthink simple tasks, reserving heavy, expensive computation only for the problems that truly demand it.
And this leaves us with a provocative thought to ponder. One, based on the open questions the researchers themselves are grappling with at the end of this paper. As we discussed earlier, the data imbalance experiments here were mild. Math data never dropped below a few percent of the total training mix, and we saw that the model could handle both math and computer navigation beautifully.
But as we look to the future, scaling models to trillions of parameters, what happens to catastrophic forgetting at extreme data ratios?
Right. If a highly specialized domain makes up less than 1% of the massive data set, will this uniformly superior performance across diverse tasks still hold?
Or will we hit a fundamental architectural limit where a single model simply cannot be both a math genius and a flawless computer navigator without completely siloing its weights into separate, disconnected subnetworks?
It is something for you to seriously consider as you curate the data mix for your next massive training run. A fascinating architectural problem to solve. Thank you for tuning into this deep dive on AI paper podcasts. We'll catch you on the next one.